So quantum numbers is actually one of my favorite topics. And the reason it is because while it may seem hard at first, once you learn the rules, it becomes very easy and you can pretty much do any problem very simply. So in this video, we'll talk about these four quantum numbers and the rules. So let's talk about the first one, which is the principal quantum number, n. This is called the shell, and it starts at 1, and it can range on technically to infinity. And it determines the electron's average distance and energy from the nucleus, so how far it is from the nucleus. So you've actually seen this concept before. Electrons that are very close to the nucleus have small quantum numbers, so principal quantum numbers. So this would be n equals 1, and as we move further out, this is going to be n equals 2, and n equals 3. And as we move outward, the energy of our electron increases, as well as the distance. So that's principal quantum number. Very simple, nothing too crazy about this one. The second one is called the angular momentum quantum number, and it's denoted by the letter L. And we call this a subshell, whereas the previous one was shell. Now, the most important thing to know is that L ranges from 0 to n minus 1, okay? And it determines the shape. So subshell is all about shape, whereas shell is about distance from nucleus. So really, when it comes to practice problems, this is what you need to know. The first shell, which is n equals 1, has only one subshell. Because if n equals 1, then the only possible values of L are 0 to 1 minus 1, which is 0. So the only possible value is going to be 0. And that number 0 represents one subshell. It might sound confusing right now, but let's do the second one. The second shell, n equals 2, has two subshells. Let's see why. If n equals 2, then L ranges from 0 to n minus 1, which is 0 to 2 minus 1. So the two possible values of L are going to be 0 and 1. Each of these numbers represents a subshell, 0 and 1. We'll talk about which subshells they represent. So there's two numbers, two subshells. The third shell, n equals 3, has three subshells. Well, if n equals 3, L ranges from 0 to 3 minus 1, which is 2. So it ranges from 0 to 2, so it can either be 0, it could be 1, or it could be 2. Three numbers, three subshells. So it turns out these numbers have meanings. So if L equals 0, that corresponds to a subshell called S. So we call it the S subshell. If L equals 1, that corresponds to the P subshell. If L equals 2, that corresponds to the D subshell, and finally L equals 3 corresponds to F. You have to memorize this. You need to memorize this for your exams, as well as the fact that L ranges from 0 to n minus 1. This is not something that will be given to you on an exam, so you have to commit it to memory. So what do S, P, D, and F subshells look like? It turns out that they have different shapes. So an S subshell looks like a sphere. A P orbital, or P subshell, looks like an infinity symbol. D looks like four-leaf clover, and F has 6 little lobes here. Right? So basically, as you move from P to D to F, you add an additional 2 lobes. S is just a sphere. Here you see the term orbital. We'll talk about orbital in the next number. All right? So just remember the next the next quantum number. So just remember that the first quantum number was shell, the second quantum number is subshell, and the third quantum number tells you the orbital, ML, magnetic quantum number. And ML ranges from minus L to plus L. So notice how all these quantum numbers are related to each other. They're dependent on one another. And it describes the orientation of an electron's orbital. So the S subshell, which is L equals 0, only has one orbital. Why? Because ML only ranges from negative L to plus L. And so if L equals 0, then the only possible value of ML is 0. But what if you have a P subshell and L equals 1? Well, a P subshell will have 3 orbitals because the different possible values of L are going to be, L equals 1, so the different possible values of ML are going to be from negative 1 to positive 1. So that's negative 1, 0, and positive 1. So 3 possible values, each number represents one orbital. Similar logic as we used last time. Okay. The D subshell, L equals 2, has 5 orbitals. Okay, so at this point you probably can guess what this is going to be. It's going to be negative 2, negative 1, 0, 1, and 2. Each number represents an orbital, 5 numbers, 5 orbitals. And finally, F is going to be L equals 3, so ML ranges from negative 3 to positive 3. So negative 3, negative 2, negative 1, 0, 1, 2, and 3. All right? And a lot of times we write these orbitals as little lines. So an S subshell has 1 orbital, a P subshell has 3, D has 5. Oops. 1, 2, 3, 4, 5, and F has 7. Okay, so 7 here. Each orbital contains 2 electrons. Often they're written as these arrows. So the S subshell can only contain 2 electrons. The P subshell contains 3 times 2, 6 electrons. D contains 5 orbitals times 2, 10 electrons, and the F subshell contains 7 times 2 electrons, which is 14. Right? So that's important to keep in mind. Right? So the last number is the spin quantum number, ms, and there's only 2 possible values for this guy. It's either going to be plus a half or minus a half. So notice here that the spin quantum number is actually not dependent on any of the other quantum numbers, and it's the only quantum number that stands alone and is independent. So each orbital, as I mentioned before, contains up to 2 electrons. You cannot have an orbital that has any more than 2 electrons. One will always have a positive spin, so that's going to be your upward arrow, and that's going to be plus 1/2. And then the other electron is going to have negative spin, and that's going to be minus 1/2. So one's always got to be spin up, and the other is going to be spin down. So let's apply all these rules to a few problems that you might see on your exam. All right, so write the subshell notation, for example, 4D, and the total number of electrons. So we got to do both subshell notation and total number of electrons that can have the following quantum numbers if the orbitals of that subshell are all filled. So let's start with the first one, n equals 2 and L equals 0. Right? So this first number in 4D represents the principal quantum number. So to write the subshell notation, we just write 2, followed by a letter. How do we figure out what letter this is? Well, we need to figure out what L equals 1 corresponds to. So whenever I do these types of problems, on the corner of my sheet of paper, I always write this, so I don't make any mistakes. I write the possible values of L are going to be 0, 1, 2, and 3. And what that corresponds to is S, P, D, and F. And I know that S has 1 orbital, P has 3 orbitals, D has 5 orbitals, and F has 7. So that way I really know my total number of electrons, as well as which L value corresponds to what subshell. So I would write here L equals 1, this is going to be 2p. Because it's in a p subshell, the maximum number of electrons I can have is 3 times 2, which is 6 electrons. Right? So we do the same thing for part B. N equals 5, so I'm going to write 5. When L equals 3, that means you have an F subshell. And within any F subshell, no matter what the principal quantum number is, within any F subshell, you can have a maximum of 7 times 2, or 14 electrons. All right, so you can do the same thing for C. So N equals 4, so you write 4. L equals 2 corresponds to a D. Let's get rid of this guy. And so in any D subshell, you can have a maximum of 5 times 2, which is 10 electrons. And then finally here, n equals 1, L equals 0, that's going to be 1s, 2 electrons, because an s orbital can only accommodate 1 orbital for 2 electrons. All right, so let's try the next example. So the next example says, which of the following combinations of quantum numbers are allowed for an electron in an atom, and which are not allowed? All right, so some of these will be okay, some of them will not be okay. We have to identify which ones work and which ones will not work. So let's start with A. So n equals 3, okay? And then they say L equals 3. Okay, let's see if that makes sense. Well, if n equals 3, what are your possible values of L? Remember that L ranges from 0 to n minus 1. So then would it be possible for L to equal 3? The answer to that is no. All right, so this is not allowed because the maximum value of L would be 2. So we'd say no because L can only range from 0 to n minus 1. And in this case, n is 3, so there's no way L could also be 3. So A is not allowed. Let's check out B. It says n equals 4. All right, so that means the possible values of L are going to be 0, 1, 2, and 3. So that's okay. Right? So then you look at the value of L. What are the possible values of ML given that L equals 2? Well, remember that ML ranges from negative L to positive L. So the possible values of ML are negative 2, negative 1, 0, 1, and 2. So ML equals 1, that's okay. And then MS equals plus 1 half, totally fine. This one totally checks out, so this one works. This is allowed, so yes, it is allowed. Let's try C. It says n equals 4, right? L equals 2. Okay, so it's just like example B, so that works so far. And then they tell us that ML equals 3. Well, wait a second, let's look at L again. ML ranges from negative L to positive L. Remember, that's the rule that you have to remember. So ML can only be negative 2 to positive 2. Here, ML is 3. So this does not work. Right? So this is what doesn't work. And up here in A, the L equals 3 was what made it impossible. So here we would say no. And the reason is because ML ranges from negative L to positive L. And in this case, it's outside of that range. So that's not going to work. So C is not going to work. And then we look at D. N equals 2. Okay? And then they tell us L equals negative 1. So then what you should be thinking is, can L ever be negative? Right? Remember that L ranges from 0 to n minus 1. L is never negative. All right? So that's a rule you should also remember. So no, L is never negative. And so D will also not work. So the only choice that works is answer choice B. And so those are two examples of quantum number questions you might see on your exam. And if you really understand and memorize those rules for each quantum number, you should be able to answer any type of quantum number question that you'll see.